NewSpace, thanks a lot for being able to present to us. Nikkei and Philip, over to you guys. And I hope everybody had a coffee so that they're ready to pull all their attention to the session again. Thanks. Over to you guys.
Hi, everyone. I just want to confirm that you can see my screen.
Yes, we can see the screen.
Okay. Hi, everyone. My name is Nikkei Ackerman, and I'm joined today by Philip Boyson, and we are both design engineers at NewSpace Systems. Just a little bit about ourselves. As I said, I'm a mechatronic engineer at NewSpace. My roles at NewSpace involved our sun sensor calibration software and optical simulations. And my main focus is next generation firmware development. And yeah.
Hey everyone, my name is Philip. I'm a mechanical design engineer at NewSpace Systems. My main roles is basically mechanical design and problem solving. We usually generate quite a few problems as well. My main focus is the sun sensor project and the next generation mechanical design. My special attribute is I can only remember memes from 2010, nothing after that. So today we'll just go through a couple of use cases. I think first, Nikkei will just talk about NewSpace Systems, the products we develop, just to give you guys an overview of what we do. Then I'll go through a bit of the space environment, what we design for. And then we'll go through the use cases, which will be Ansys Zemax. This is mostly on Nikkei's side, the optical design of this product, and then also Ansys Mechanical, which would be me that's going through that. That's the mechanical design and the simulations we did to design this new generation of sun sensors.
So just a little bit about us. We supply, at NewSpace, we supply a range of attitude, determination, and control products. In our range, we have actuators, sensors, and navigation instruments. For our actuators, we sell reaction wheels and torque rods. Sensors, we have a magnetometer and a sun sensor, which you will be hearing a lot more about today. And then we also sell GPS receivers and antennas.
All right, I'll just go through the space environment, just this basically the loads that we design for. First up would be vibration and shock. So during launch of a rocket, there's a large component of vibration, and this usually consists of sine vibration and random vibration. The sine vibration is due to basically acoustic energy propagating through the rocket, and it's usually low frequency, so around 50 to 150 hertz, and these are large amplitude vibrations. We then have random vibrations, which is in the frequency from 20 to 2000 hertz. This has a big implication in terms of fatigue on your product. If you do have modes in that frequency spectrum, you just need to design for fatigue during that vibration period that the product is going up in the rocket. Next is the shock. That's usually when you jettison your product or the rocket separates. There's a big shock wave that propagates through all components. So you just have to design for that as well. This is usually a big forces that are transferred onto your product. So for this reason, we just analyze that as well, and we test for that as well. Then we have thermal vacuum. Of course, there's no air outside in space, so all of the components are in vacuum. And one of the big things we look at is outgassing compliance. So when a product is in space, it tends to outgas any entrapped water or chemicals that were introduced during the manufacturing process. This can contaminate sensitive instruments like optics and so on. So that's a big consideration. And then we design for thermal radiation and mostly conductance for the space environment. There's no air, so there's no convection that happens. Then there's quite a bit of temperature cycling. If your satellite, depending on the orbit, you orbit around 16 times a day around the Earth. So that translates to about 30,000 temperature cycles in about 5 years. So that's a big consideration for us. We want to design our product robust against those thermal cycling. And what we see, what we design for usually is temperatures from around -40 to 65. This does depend on the satellite and the mission and how the satellite manages its heat. But we found that the -40 to 65, 70 degrees is usually sufficient for most satellite designers to work with. Then we have radiation in space. This is mostly a problem for electronics, where the electronics start to fail after a certain amount of radiation that it's been radiated to. You also get single event effects where a bit is flipped, which can cause some trouble with your software. This is mostly on the electronic side. And then also we do EMC. We design for EMC, radiated and conducted emissions. You don't want your product to interfere with the other products on the actual satellite. But we won't be talking about that too much today. Right.
So, as we've heard a lot about today, Zemax OpticStudio offers advanced ray tracing algorithms to simulate light behavior in optical systems. And this enables us to design complex optical systems that includes lens optimization and materials and coatings. The software allows for easy performance of tolerance iterations, which assesses the impact of variations in the optical system's performance for overall design robustness and manufacturability. Additionally, Zemax OpticStudio supports interoperability with other design tools, facilitating easy integration. Its multi-physics simulations capabilities allows for comprehensive investigation into real-world scenarios, including thermal and pressure environment changes. So let's look at one of these real-world scenarios. As soon as my slide changes, there we go. So the NewSpace Systems Aquila DO1, or Gen 1 from now on, is a flight-proven system with extensive in-orbit heritage. To date, over 400 sun sensors have been delivered globally, and it's baselined on 5 constellations. The sun sensor consists of a digital sensor with a linear array of photosensitive pixels, a lens stack, and a metal mask with slits cut into it. As light passes through the mask and projects a pattern onto the detector, creating a one-dimensional brightness profile containing 4 or 3 strong peaks that is then used to determine the sun vector. The Aquila Sun Sensor is currently one of our highest volume products in production. In 2022, the linear photosensitive array became obsolete, prompting an investigation into designing a replacement sun sensor. As the demand for the Aquila sun sensors are high, the urgency for a replacement product was evident. This led to the conceptualization of the Gen 1.5 Aquila. The technical requirements for the Gen 1.5 were to identify a new detector, integrate the new detector, but have the Gen 1.5 be identical to the Gen 1 in form, fit, and function, improve the manufacturability of this product, and do all of this without disrupting the existing embedded processing and calibration algorithm too much. To our relief, we were able to identify a replacement detector. However, these detectors were not identical. If you take a note on figures 1 and 3, the new detector had a very different optical structure. Where the old detector array was potted in a clear glass, the new detector had an air gap between the pixel array and the covered glass of the detector. Additionally, there were variations in the photosensitive area of the detector. This prevented us from integrating the new detector as is, necessitating further design changes to accommodate the newly selected detector. However, as previously mentioned, to adhere to the form, fit, and function limitation and to minimize the risk of disrupting the embedded or calibration algorithms, we needed a better understanding of how these design changes could affect the product's performance. Therefore, we decided to simulate the new changes. We used Zemax OpticStudio to simulate the design changes to our sun sensor, ensuring precise performance and reliability. This tool allowed us to efficiently validate the new design iterations. Our system setup comprised of three main aspects: the optical stackup, the detector, and the light source. Building the optic stackup was straightforward. We easily imported the housing CAD models and selected materials and coatings, and the glass and material catalogs enabled us to use data from multiple vendors and import our own material data. Setting up the detector was simple, allowing us to specify the wavelength region of sensitivity. And for the light source, Zemax enabled us to select a light source for which we could specify the spectral properties and geometric and photometric properties to closely mimic actual sunlight, as well as our optical test bench to provide comparable data. We were able to use the ray tracing capabilities of Zemax to allow the rays to propagate through the system in any order. This allowed us to identify where light could scatter, reflect, or refract within the system, disrupting the one-dimensional sun image we expect to see. The ray tracing provided a variety of output data, which could then be compared to expected outputs. Before we get into the results of the simulations, I just want to give a brief overview of the format of the results. For our specific application, we are mostly interested in the radiance of each detector pixel, which for the remainder of the slides will be represented as peaks. From this data, we are able to obtain the one-dimensional sun vector image. The x-axis represents the individual pixels on the array, and the y-axis represents the radiance on each of those pixels. These peaks are then used by the sun sensor to calculate the sun vector. The position and quality of these peaks are truly the cornerstone of the performance of our sun sensors. From the ray tracing, we were able to obtain our one-dimensional sun image and compare these images to known sun vectors. We were able to control the input angle of the light source, iterate our optical stackup, and detector placement for an output that was almost identical to our Gen 1 sun sensor. There were multiple configurations we considered. I will only be going through a few of them. For our first configuration, we considered using the detector as is with the previously mentioned air gap. On the figure shown, the orange line represents a known sun vector and the blue a simulated image. At small angles close to bore sight, the sun image was very similar to the Gen 1. However, at large angles, the air gap and detector lens refracted light, yielding much different sun images. Another configuration we considered was using the detector as is, but changing the thickness of our thickness and material of our lens stack-up. This also had little to no influence on small angles within the field of view, but again, changing the thickness and material of the lens was not enough to correct the refractive offset caused by the new detectors. At the time, changing the lens shape was not a viable option due to the space constraints within the unit. After some more design iterations, we found that the solution that mostly identically mimicked our Gen 1 performance over the entire field of view was removing the lens of the detector and filling the air gap with the same adhesive to bond the detector to the optical window. We then built some more prototype units with the new optical stacker. The above graph shows the error distribution over the field of view of the sun sensors from our first prototype in comparison to our Gen 1 reference unit. Although our first unit was not quite as accurate as our reference unit, it was still well below our 0.2 degree error limit. This is just another way we can represent the RMS error of our sun sensor over the field of view. As you can see, we saw very similar behavior over the entire field of view as our Gen 1 sun sensor. Since our first few prototypes, we have built a few pre-qualification prototypes for which we have been getting consistently good results. In conclusion, we learned that conducting preliminary conception simulations at the conception stage can significantly save time later in the design process. We also learned some more about our own sun sensor, and there are some things we can improve in our future designs. Future simulations we can also do is, due to the simplicity of our current lens design, we were not able to fully utilize Zemax's extensive library of common lens designs and glass catalogs, and this could definitely benefit us for future generation designs. Zemax also offers thermal models that allows us users to see how thermal and pressure environment changes affect the refractive properties of materials. This could help us enhance our thermal compensation in the calibration algorithm in the future as well. I would like to thank you for your attention and hand over to Philip, who will be looking at a mechanical focused case study.
Thanks a lot,
Thanks.
Nikki. Is there any questions before, as Philip is transferring this to his screen? Any questions now? No, I think, Philip, you're good to go ahead. Thanks a lot for that, Nikki.
I just want to hear if you guys can see my screen.
Yes, we can see it.
Okay, great. Thank you. Okay, so I'll quickly run through our Ansys mechanical case study. So just to go through the contents, Ansys Mechanical it's a powerful FEA software that we mostly use for structural simulations, structural and thermal simulations. So I'm going to go through just the design inputs that we use for while we do our development. I'll go through the static simulation where we basically pre-stress our unit. Then I'll go through a modal simulation where you extract your natural frequencies for a specific product. Then a random vibration analysis, which gives you stresses and responses for your unit. And then also a shock analysis, which gives you more or less the same results as random. And then a thermal analysis as well, where you can analyze mostly the critical electronic components, what temperatures they will reach, and how the heat flow propagates throughout your product. So just to go through the design inputs, it's very important, from through the years, for me, I've realized that having a good requirement spec at the start of a project is very important, so that you can understand the loads that you have to design for. Usually this requirement spec comes from either a client or market research. For us, we have, as design inputs, we have static loads. This is usually from the constant acceleration of a rocket. This is usually quite small forces in comparison to the vibration loads in our case. And because our products are quite small, they don't have large torques due to these constant accelerations. Then we have vibration loads, which is the sine vibration that I spoke about earlier, which is dependent on your launch vehicle and also the satellite that you mount your product on, and your random vibration, which is usually given in a power spectral density graph. This is as well dependent on the satellite and the rocket that you launch. You then have shock loads, which we usually have a industry standard profile that we use for analysis and testing. And then, of course, thermal loads. This is usually the component heat generation on the electronics itself. And then you have, in space, you have solar radiation coming in, heating up your unit. And then you have your satellite environment. So the sun sensor is mounted on the outside of the satellite. So it does get solar radiation, but it also emits radiation into space. And then lastly, materials. It's always a bit of an issue setting up materials. We currently use Ansys Granta, which is just a big catalog of materials, and it integrates very easily with Ansys Mechanical. So you can search for a wide variety of materials, and they usually have all of the properties needed to do your simulations. All right, so I'll run through the first step in our analysis. Usually is doing a static simulation, and this is basically to pre-stress our product. So when you bolt down your product, it pre-stresses the materials, which usually changes the stiffness of your product, which will in turn then also change your modes, at what frequencies your mode shapes happen. So this is basically what we do. This is the first step in our static structural. You'll see on the left is my simplified model of the product itself. And in this case, I actually modeled the little bolts as well, a very simplified model. There are different methods of doing this. For this presentation, we're just going to use the actual physically modeled bolts so that we can actually see the stresses inside the bolts. We can analyze those bolts as well as we go along with the simulations. Bolt analysis is quite difficult, quite complex. So this is usually our first order analysis of the bolts, and then after the simulations, we'll do a bit more analysis of the bolt loads and fatigue and so on. So yeah, the first step is then defining a preload in your bolts. It's usually from the torque and the bolt size. Just for reference, this is M2.5 bolts, and then over at the top here it's M2 bolts. Just to give you an idea of the size of this product, it's around 40 moles by 30 moles millimeters in size, and around 20 millimeters high. So it's a nice and small product. Okay, so after we've done this pre-stress static simulation, we then go into our modal analysis. So the modal analysis takes the pre-stressed static simulation as input, and then we, one of our goals for our product is to have no natural frequencies within the 20 to 2000 hertz range, and the reason for that is that frequency range is where most of the vibrations occur during launch. Any frequencies higher than that is usually damped out in the structure of the rocket. So for this part, because it's very small, we can luckily design out any modal, any natural frequencies higher or in that range. So just to go through an example here, we have a component that's bonded onto the lens there, and we had a look at two adhesives. And I'm just gonna, I hope this video comes through okay. I saw it was a bit laggy on the previous slides. But basically we had our first mode. For adhesive 1, it is very close to our actual testing frequency. The second mode and third mode is slightly out of the test frequency, but this doesn't take into account all of the temperature variations and material variations you can get. So we want to be quite far out of this frequency range for the specific part of the design. So adhesive number 2 was the one that we went for. It was just a bit stiffer adhesive, which pushed out the natural frequencies for this component into the 3000 hertz range. So of course, this is a simple example, but your geometry and materials and mass and all of that plays a big role in these model shapes. So iterating through the design and doing these analysis helps quite significantly at the onset of the project. All right. After the modal analysis, you then go on to the random vibration analysis. It takes that modal analysis as input. The important thing is that you have to do your modal analysis and extract frequencies at least a bit higher than your PSD input frequencies. So in our case, we did an analysis up to 3,500 hertz, but our PSD only goes to 2,000 hertz. So you give it the modal analysis as input. You specify your PSDs, which is from your requirement spec in the X, Y, and Z directions. You then run your simulation, and what I usually like to do is just use the response probe in Ansys. So you can select a vertex or a point on your product, and in essence it puts down a virtual accelerometer, and you can check the response that you get at that point. And I usually use this to just check that the input I give is actually shown as an output as well. For sections of the model that does not have a natural frequency. So it's basically moving at the same acceleration as the input. So what we then do is we do get static, not static, we get stress analysis results from our random analysis. We then have to sum that with our static analysis, because Ansys only evaluates the random stresses. So you then end up with your stress plots. As shown here, what I like to do is I group my product into material groups to do, easily analyze each of these material groups as we go along with the simulation. For this example, we're just going to go through this is our aluminium group of materials. We have the simplified bolts, which in this case is stainless steel, and then we'll have a look at that adhesive layer as well. This is on the right here, that very complex rectangular shape. So you'll see we get these stress plots. In the shock analysis, I'll show you how we usually go about doing a margin of safety plot as well. That's much easier to then visually see any sections in your product that might give you problems or might yield from a material materials perspective. Then in Ansys, you can also do a fatigue analysis after you've run your random simulation. The fatigue analysis tool gives you two properties that you can plot. The one is the expected life. So this basically gives you the expected life in seconds for what your product can survive at the levels that you specified in your random simulation. For this product, you'll see that we have a very, very high life. And this is because the stresses are quite low for this specific product. When you do have resonances and you have a larger structure, this is a very important tool to use to just do your fatigue analysis on these random vibrations destroy products quite quickly. You then have your damage feature as well that you can run, and the damage basically gives you a ratio of the design life divided by the available life. So it's your exposed duration divided by the available life. So we're looking for a very small number here. If that number is 1, it means your product will basically survive one design cycle or one timestamp of your design input. So we want a number much lower than that. And for this product, we don't have an issue. It's a very low number. Our design criteria is usually 0.25. So that's it for the random vibration. We then go on to do a shock analysis. This is in Ansys called the response spectrum. It also takes in your modal analysis as input. What is important as well for this is to just dependent on your response spectrum spec that you have to include the necessary frequencies in your modal analysis. So for us, our shock response spectrum goes up to 10,000 hertz. So we just did our modal analysis up to 10,500 hertz just to add a bit of margin there. You can then in Ansys specify your SRS, your shock response spectrum for the X, Y, and Z directions, and you click the simulate button. We then, for this case, also have to sum the static analysis and our shock analysis stresses. And then you get a very similar stress plot that you get for random. It is usually much higher though in value. And then what I usually like to do is I like to do a margin of safety plot in Ansys as well. So in Ansys, you can specify a user-defined result, and you can input, any of the extracted data and apply an equation to that, and then plot it over your full design to see, to visualize the results much easier. So basically, what I'm showing currently is our margin of safety, which is, if you look at let me just get my laser pointer here, which is basically this formula where we have our allowable stress. This is from your material. So, basically we use our yield stress for this. Then you have a factor of safety, which usually comes from your industry and your internal design criteria. And then you have your applied stress, and then you just -1. So you then get your results. Anything above 0 means you have positive margin on your design, and anything below 0 means that it's basically a fail from your criteria. So you'll have to relook at that part of the design. So it's just a nice and visual way to quickly see if there's any areas in your design that's going to have issues. For the example we have here, the aluminium group seems to be fine. We have a minimum of 0.5 margin of safety. The bolts here is very close to 0, so this is something to be concerned about. If you look closely, you'll see there are little red spots on these larger bolts, which usually indicates that you have a bit of a mesh issue. So you can refine your mesh a bit better at those locations to get more accurate results. And then also this depends on how you modeled your bolts, you know, if you use the pitch diameter or the minimum diameter and so on. But it does give you, you know, please focus on this location input. And then for the adhesive, we have good margin as well. All right. You can then also in Ansys extract the bolt loads, which you can use for your bolt analysis in a different tool. As far as I know, Ansys doesn't have built-in features for, you know, a complex analysis of bolts. So we use an external tool for that. All right, and then I think next we'll just go through the steady-state thermal analysis that we usually do with during the design phase as well. So we want to analyze the temperatures of all of the critical electronic components within our assembly. If any of these components overheat, it means the end of the product. So it's very important to evaluate these components and to thoroughly test them to see that your design meets the spec. We use the analysis tool to also evaluate the thermal paths that the thermal energy follows throughout the product. For this analysis, we have the following inputs that we give the analysis. First of all, it's the thermal environment. And for us, that's the mounting interface temperature. So this would be the satellite temperature, basically. A lot of our products conduct most of its heat actually into the satellite mounting surface. That heat is then dissipated in the thermal control of the satellite. They usually have radiators or heaters, you know, for cooler temperatures as well. So we have that interface as input, and then you have your thermal radiation environment. This is for the case of the sun sensor, it can radiate heat into the vacuum of space. We then have heat sources. This comes from the electronics. The design engineers for the electronics should be able to give you the power consumption for the critical components, the high power consumption components. This power is dissipated within the junction of the electronics. And there's usually a bit of resistance, which I'll get to just a bit further down. The other heat sources we have is solar radiation, so radiation coming from the sun when the unit is in the sun. It gets heated from the sun. We also have a bit of reflection from the earth. So the rays hitting the earth, the sun rays hitting the earth and reflecting back onto the product. This also heats up the product a bit. And then the last items that we have to specify as input will be your thermal resistances. So we have a lot of junction to case resistances in the electronics. So this is usually specified in the data sheet for the electronics. It's basically the resistance between your silicon die onto the package mounting surface. And this is very important to also model while you're doing this simulation. It usually forms part of a big resistance flow for the heat. So just assuming that the heat can flow freely from the chip into the board and then out into the mechanics is a bit of a mistake. Then you have contact resistances, you know, on all of your mechanical joints that you also need to take into consideration. All of these inputs are quite easy to set up in Ansys. And then As usual, you just press your simulation button, and then you can analyze your results. So one of the things I usually like to do first is to do a heat flux analysis to visually see how the heat flows in your product. You'll quickly see errors in your setup doing this. If you've made mistakes with contacts between some of your components, you'll see that heat flows in an unintuitive way from one component to another. And I'll just show you here what this looks like. So this is usually how you can visualize your heat flow so this is the heat flux from one of the hot components in our assembly, and you'll see this same video. It's just a side view, and you'll see that we have most of the heat flux going into the mounting surface, where the product is bolted onto the satellite. And then we also have a few watts basically being irradiated out into space. And it's very interesting to play around with your radiative surface properties for these components. So it's always a big design choice with what surface coating you go with for your product. For this product, we had a look at gold, and which was the surface coating used in our first generation of this product. We compared it to black anodizing, and we found that black anodizing had superior thermal properties for the space environment. But the analysis allowed us to easily play around with those properties and see what effect it has. And then, of course, you can have a look at your final temperatures. This example gives just a side view of some of the electronic components inside our product. You'll see over here is one of our hot components, and you'll see a big jump in temperature from this red section, which is how I modeled the junction, and then our PCB, and then again from the PCB to the mechanics, from the mechanics to the basically the boundary condition. These big jumps, and those are the thermal resistances I spoke about. So it's always a good way of just checking that your thermal resistances are set up correctly. And then, of course, you can see the temperatures that your product will see and what the electronics will see, and you can compare this to, the max junction temperature that the chips can allow. This also allows you to choose packages of these chips, because many of them do come in variants that has better thermal conductivity into the board, or that have higher junction temperatures. So this analysis is always extremely helpful during the design phase, and it helps during the PCB layout, going backwards and forward with the electronic engineers as well, to analyze how the heat flows in the product and how to get rid of that heat. And then lastly, I usually just have a look at the method of the mechanism of the heat conduction. It's always good to see where most of the heat flows. For our example, it's more or less a 50% split between the heat is conducted into the satellite bus, we call it, and then also radiated into space. This radiated component, of course, changes quite a bit depending on what direction your sensor, your product has in space. If it's looking out directly into the vacuum of space, it'll radiate very well. If 50% of it is pointed towards Earth, it won't radiate that well. So we always want a good conduction path as well. And that's it's very easy to check in Ansys as well to just remove your radiation component and see what effect that has on your final temperatures that you have in your product. Yeah, so that's it from my side. Just a quick summary of how we use Ansys tools to analyze our products and iterate through the design.
Thanks a lot for that, Philip. I think it was very good and well delivered, and a lot of effort has gone into this and putting it all together. So thanks a lot. Is there any questions?
Just for interest's sake, Philip, how well is the random vibration spectrum defined? Do you guys get a good input, or is it kind of a guesstimate?
So it depends. If you work closely with clients, they can specify your random vibration input very well, either by testing the actual physical mounting on their satellite or by simulation as well. So from that side, we usually get a good, accurate specification. If we don't have a client that specifies our random or PSD, we have kind of over the years built up a catalog of the expected random vibration inputs that we'll get, and we then base our specification on that. We try to envelope most of our clients' vibration inputs.
Okay.
Hope that answered. Yeah.
Yeah. Thanks, Philip.
Okay, I think there's another question from Neil de Breer.
Yes, so the question is maybe more towards the first part of the presentation.
Yeah.
But what is the field of view and the accuracy of that, and do you have optics forming an image onto the sensor, or I don't know if they could elaborate a bit on that?
So our sun sensor has a 140-degree field of view, and our sun sensors are also rated to a 0.2 degree RMS error, but we do get 0.1 as well. Now, the image that we see on our detector, as I've mentioned, our optical stack-up has a metal mask with slits cut into it, and as the light falls through, it projects those 4 slits onto the detector, either providing a 4-peak image or a 3-peak image.
Okay. Thank you.
Okay, I think there's another question from Craig. You can go for it, Craig.
Could you maybe explain more about the working principle? So how the 4 slits are used to calculate the angle, or how they're related to the angle or the sun vector, or whatever the measure is, and the orientation of the slits. So is it a crosshair that you showed, like that crosshair in the beginning, or are they 2 crosshairs, or how does it work?
It's 2 crosshair slits, and one is in the Y direction and one is in the X direction, and then we use those to determine of the peaks we've identified the offset from the center of field of view.
In some of the graphs that you had 2 or 3 peaks, or
yes.
So were they overlapping, or?
Yes, those were peaks that were overlapping.
Okay.
Okay, looks like another question from Andre. Andre, you can go ahead.
Yeah, Philip, the last slide you showed, can you just show that again? I saw 3 strange things in your slide. It looked like coils.
Okay, just hold on, let me get that up.
Yeah, those brown or What are those?
Oh, this end slide. Okay, let me just get my laser pointer here. So you're referring to these
Yes.
these components here. Those are our magnet talker rods. So they're basically a copper wire coiled around a magnetic core. And what we do with these is if you apply a current, it generates a magnetic field, which then interacts with the magnetic field of the Earth. And you, by orientating them in the the X, Y, and Z directions, you can then control your satellite with these magnet talker rods and the reaction wheels. When they work together, you can finally control your satellite. I think the other thing that they are used for is basically adding resistance, almost like rotational resistance of your satellite. If it's tumbling after it's been released from the rocket, you can engage or power these magnet talker rods, and they interact with the magnetic field of the Earth, slowly slowing down the actual satellite.
Thank you very much.
Thanks for that, Philip. Is there any other questions? Still have NewSpace here online. If there's any questions.